interpolation. I prefer the term optimal interpolation to kriging simply because it describes what it is that is actually going on. A lot of the folks who use this use it only for interpolation, but it's much more powerful than that. And hopefully by the end of the day today, you'll agree that this can be useful for a lot of other things. To give a little bit of background, a little historic, I love to do historical geology and geophysics. The people who are involved in this, it's called kriging because the individual who first came up with the idea to do this was a master's graduate student in South Africa by the name of Danny Krieg, who essentially was interested just in a very practical problem of how do you sort of extrapolate what the ore grade is when you're looking at mining data. So if you have a bunch of measurements of mining grade and you want to have some sense of where you want to focus your attention going forward, what would be the way that you would decide is the best direction to go with further mining, for example? So he worked on using statistics to get at this problem and came up with what was really a fairly brilliant idea for describing the statistics of measurements and using them then to make predictions about what the variation of those fields might be in other places where you don't have measurements. Those ideas then came to the attention of a French mathematician, a fellow by the name of Georges Mathurin, who went on to develop sort of the foundations or the fundamentals of the ideas underlying what Danny had done, and that came to be the basis for what we call geostatistics. One of the important concepts that came out of that was what we call a regionalized variable. This would be a variable that has properties that are sort of somewhere in between deterministic and truly random, which is to say that you can make some prediction about what a variable might be by knowing some, or what the field might be by knowing some information about the field, but it's sufficiently random that you're never going to be able to perfectly determine what that is going to look like at any given location because of processes that might be very complex or that you might have sampling that is insufficient to give you real predictive power. Those regionalized variables are what we now call in signal analysis a stochastic process. And there are a lot of relationships between what we do with geostatistics and what we do more commonly in signal analysis, which a lot of you as seismologists may be more familiar with. Correlation functions, power spectra, and such are related to this. It's just a little bit of a different formulation. All right, so what's the basis for this? First of all, you need some sort of a statistical representation of the medium or the field that you're going to be looking at. That statistical representation in geostatistics we call one of two things: the semivariance or a variogram, depending on who you talk to. I've been informed sometimes by reviewers of my papers that semivariance is not quite correct, and they suggest variogram instead, but I think it's kind of a matter of semantics. Basically, what it comes down to is this is a measure of the expected value of the difference between measurements as a function of the distance between measurements. Okay, so the basic idea here would be that if you've got some sort of a continuous function, some field that varies in a continuous fashion, the values of the field themselves are going to be the same at co-located points. They're going to vary in such a way that the closer you are to co-location, there's going to be more similarity, and the further you get away from being co-located, the less similar those field values might be. On top of that, of course, you have measurement uncertainty, variance associated with the measurement itself. And so both of those things should be encapsulated in a semivariance that is derived from measurements. And we do derive the semivariance for a field from measurements of the field. The way that we go about that is to basically take pairs of measurements. We bin those pairs according to the distance between them, and then we calculate the sum as an approximation of the expected value of the difference between the two measurements for all of the measurements that lie within that distance bin. And then that sum is divided by 2 times the number of the measurement pairs, and that gives you the semivariance, or the variogram. The little image here is basically showing you sort of a stylized or an idealized case where you've got distances between possible pairs of measurements that range from delta 1 up to delta 4, depending on those distances. And so basically you would just bin according to whether it's a shorter distance or a longer distance, do these sums and evaluate your expectation operator in that fashion. Here's an example from a paper that we published about 10 years ago. Basically, this is an image of the seismic velocity ratio for the crust for data that were taken out of the EARS database. For those of you who are not familiar with EARS, basically that is a automated routine for developing receiver functions from seismic data from earthquakes. And then those receiver functions are stacked in a parameter space for the crustal thickness and the seismic velocity ratio, VPVS, as a means of basically sampling those receiver functions at the times that would be predicted for a given combination of seismic velocity ratio and crustal thickness. They're noisy data, notoriously. And this is an image of what those noisy data look like for the seismic velocity ratios. But they do have some statistical relations that are sort of significant. And so over on your right-hand side here, you'll see that there are variograms for the raw EARS data for crustal thickness on top and for the seismic velocity ratio on the bottom. And you do see that, in fact, they're more similar as they get closer together, less similar as they get further apart. There are actually 2 variograms that are being shown here, and the reason for that is that one was for the raw EARS data, and the slightly lower variance case is an example of what happens after we had run an inversion that used the spatial statistics and also gravity data to try and improve those measurements using these HK amplitude stacks, as they're called, to come up with estimates of these fields. All right, so
before we move on, we have a question.
Yes.
So the question is, does the variogram relate to a correlation length for random fields?
Yes, it does. And in fact, you'll note that there are two things that are shown on these images. One is the red dots, and those are the actual binned measurements that were taken from, in the top case, the EARS measurements, and in the bottom case, the measurements after we had modified them. The blue line is a model. And so what we've done is we fit an idealized model to those binned values in order to come up with these estimates. And now I've forgotten what the question was again, and I'm not sure I've answered it.
So the question was, does a variogram relate to a correlation length for random fields?
Yes, it does. So you'll note that when you're very close, they're more similar. As you get further away, they become less similar, and then they kind of max out at some value. And that value at which they max out, essentially where you stop increasing the model and you've maxed out, is where you would consider the correlation length scale to be. There are different, what they call ranges associated with different models. When we get into the actual lab portion of this, We'll talk a little bit about range, but those are related to the correlation length scale. So there is a length scale at which they decorrelate, and that length scale is basically where this model stops increasing.
Okay.
All right, so that's just the first step though. And the reason that you need that information is because you do need some sort of a description of the statistical properties of variation of the field in order to be able to use that information to come up with an expectation of what's going on at a particular location. As I mentioned earlier, this was originally intended to be used as an interpolant. The form that this was done in originally is something that is now called punctual kriging, or in PyKrig, I believe the developers refer to it as ordinary kriging. This is the simplest approach that you can take, where basically you assume that there's no trend values or background other information going on, and you're going to estimate the field essentially as a weighted sum of measurements at nearby points where you have actual knowledge of what the field looks like. That punctual kriging, as I mentioned, is basically assuming there's no drift in the random variable, which is to say that there would be some trend or other background thing going on. We're going to use this one primarily because it's simpler, and because when you assume a drift, it starts doing things that maybe you don't want it to do. And as a general rule, I try not to use what they call universal kriging, unless you're looking at some very, very small sample of data. The goal in this case is to choose these weights, the W sub I, that are applied to each of the measurements of the nearby sites in such a way that you're going to minimize the interpolation error, or the estimation error of the interpolated value at that point. And so this x hat p, our estimate then, is going to be related to the true value x by some estimation error. And what we want to do is to minimize that by using the variogram representation of the statistical properties. Danny Krieg was able to show that when you then apply the minimization process that we're all familiar with, of course, where you take a derivative and set to 0 with respect to the thing that you don't know, which in this case is going to be the weights. You do a lot of algebra in this case, but what it gives you in the end is for n values at which you want to interpolate from, you'll have n equations in n unknowns, in which the equation is going to be equal to the variogram value at 0 distance times the weight at 1 plus the variogram value at the distance between measurements 1 and 2 times the W value at 2 plus, and so on up to the distance between measurement value 1 and measurement value n times the W, the weight for the nth measurement. And then for the second row, you've got delta 1, 2, gamma at 0, and so on up to gamma at delta 2n, and so on, until basically you've essentially created gammas associated with the distances between each of the measurement values that are being measured by each of the weights, or multiplied by each of the weights. And those then are set equal to the variogram associated with the distances between point 1 and, and point P, point 2 and point P, which is the interpolation point, and finally point N and point P. Of course, we would like the measurement to be unbiased. And in order for the measurement to be unbiased, we're also going to require that the sum of the weights is equal to 1, so that it doesn't stretch the measurements in some fashion in order to come up with your interpolated value. So we actually add an additional row and column with a Lagrange multiplier, or a slack variable if you prefer, where basically what we do is we set the values equal to the sum of the weights plus 0 times the slack value equal to 1. And then we add the slack value in to the relationship between each of the variograms for the measurement points and the variogram values at the distance between the measurement points and the interpolation point. And then basically we're going to solve. So you solve this system of equations. Of course, the larger your number n of measurement points, the bigger this gets. Typically what you do is you truncate to some small number of the nearest points. And then you solve for your weights, and your interpolated value then is simply going to be the sum of the weights times those measurements at each of the sites. That interpolated value is not the only information you have, though, because of the fact that you also have this model of the variance associated with each of the distances from which you've weighted your sum. You also have a way of evaluating what the expected value of the variance is associated with that interpolation. So you can actually measure, or you can estimate what you think the error is associated with that. And that, it turns out, is going to be equal to the weights times the gammas, the variogram values, at the distances between each of the measurement points and your interpolation point, plus, as it turns out, the slack variable. Okay, so a lot of math in there, a lot more than most of you probably want to deeply understand at the moment. But basically what it comes down to is this. You have a means of estimating what the interpolated value is with a minimum error. And that's this XP, the sum of the weights times the measurements surrounding. And then you have a means of estimating what the variance is, or the error is, associated with that interpolation. And that's this estimated value of the epsilon p squared. All right, so let's look at an example really quickly. This is gravity data. Over on the left-hand side, we have a map of places where there are measurements of the gravity field. These are ground-based measurements of gravity that have been taken in my neck of the woods in the western United States. You'll see that they're fairly sparsely distributed. Some places they're distributed much more densely. Other places there are no measurements in very large regions. That's because we have a combination of populated areas in valleys and basins in the region, and unpopulated areas in forested and mountain regions. But if you take all of these measurements, these are from the PACES database for gravity, and you form a variogram from those measurements, then what you find is you get something that looks like this. There are a lot of measurements in here. So this is a lot smoother than the variogram I showed you before. And it increases rather rapidly from a relatively small value. So the smallest bin here is at a mean distance of about 200 meters. There, your measurement sigma is about 1.5 milligauss. By the time you get out to 1 kilometer, that's increased to 3.6 milligauss. By the time you get to 2 kilometers, it's 5. And then by the time you're out at, say, 10 kilometers, you'll be around 10 milligauss. Out to basically your decorrelation length scale is showing up somewhere around 400 kilometers for the gravity field. If we take and we use that variogram to do kriging then of those measurements, you get fields that look like this. On the left-hand side, is the actual gravity field. Here what I've done is to drape it over the gravity gradient. The reason that I did this is because it shows up any outlier values, and these outlier values will show up as sort of point values where there seems to be something that's kind of funny going on in the shading. And those basically are probably related to the fact that the PACES gravity database it's kind of a community database where people just submit their data. And everybody does data reduction a little bit differently for gravity. Some people will use very well-defined corrections for the topographic contribution to gravity, what we call the complete Bouguer correction. Other folks might use different sort of network reference frames. And that's why you're getting these outliers. But overall, you can see that you've got an interesting gravity field. More interesting, perhaps, is what we see for the uncertainties associated with the gravity when you look on the right-hand side. And what you find is that, well, two things. One, where you've got lots of measurements, the uncertainty is lower. Nowhere here is the uncertainty as low as the smallest value in the variogram. And that's a typical feature of kriging. Because you're using sites that are further away than just the nearest site, you're always going to get something that's, by combination, a little bit larger uncertainty associated with it. So the smallest uncertainty here is about 5 milligauss. But it gets as high in some areas as about 20 milligauss. And that's because there are these sort of wilderness areas or mountainous regions where there just aren't any measurements. And so the further you get away from your nearest measurement, the larger the uncertainty is going to be because you don't have those close values with a small difference in the variogram to apply in your weight scheme to come up with your estimate. Okay, so the question that might be sort of coming to mind, though, is how is this going to be useful for inverse theory? And particularly, how is it going to be useful for something like what I'm doing, which is seismology? Well, you can apply this approach to any field that you have measurements, right? And so commonly we're dealing with spatial data when we're dealing with seismic models. Properties like the crustal thickness or properties like the seismic velocity ratio of the crust or things along those lines. And when you're doing an inversion, you found last week in the talk that was given by Steve that there are a number of different ways, of course, that you can do seismic inversion, but one of the useful things to be aware of is what's called Bayes' theorem. And Bayes' theorem basically states that you can relate probabilities or probability density functions for what the expectations are for models given data that you may have collected to the probabilities of data you've collected given some choice of model parameters to the probability of the model parameters themselves and the probability of the data, right? So in this case, I should point out that here the overbar that I'm showing is an indication that what we have is a vector. So we have some number of parameters m that are in a vector form. And the probability of those model parameters m given the data that we've collected is equal to the probability of the data given the model parameters times the probability of the model parameters divided by the probability of the data. Each of these can be represented as a probability density distribution or a likelihood function. The probability of the data given m is probably going to be something that you've framed in the context of a measurement model. That is, how well does a set of model parameters predict your actual data, for example? And one of the important things about Bayes' theorem to bear in mind, and I should step back a little bit, and I'm going to give a little history here again. Bayesian inversion got kind of a bad rap early on because it was often used by folks in industry to sort of get an answer that they wanted, or an a priori expectation of what they thought they should see. But it was an a priori expectation of what their model space should look like that was a concept in their mind rather than based on actual independent information. Whenever you're using Bayes' theorem, you want these probability density functions to be based on independent pieces of information, okay? In the case of the probability of the model parameters, here we're calling it an a priori distribution, but it should contain independent information about what those model parameters should be, okay? If we think about a case, for example, where we have a point measurement, and so receiver function HK stacks are a great example of this. Basically, when you do HK stacking for receiver functions, you're making a measurement from receiver functions at a single site, okay? And at that single site, you are basically creating a model of what the travel times should be as a function of the crustal thickness and as a function of the seismic velocity ratio. And then whatever that model predicts for the arrival times of the primary P to S converted phase and all of the reverberations, the PPPS and the PSPS and so on and so forth, you sample those amplitudes at each of those predicted times, and then you stack those amplitudes. So this is it's not really a probability density distribution, but what you would expect is it is a distribution of stacked amplitudes that should be large for the choices of crustal thickness and seismic velocity ratio that are similar to the true crustal thickness and the true seismic velocity ratio. And it should be smaller at other choices of H and K, all right? But this is for a single site. And of course, you've got other sites. So in this case, what you can do is you can take an interpolation from those other sites, and the kriging interpolation gives you an expected value, mu, for, say, the crustal thickness or the VPVS at that particular site. But it also gives you a measure of the variance associated with that interpolated estimate. And that then can be used to form an a priori model parameter distribution using multivariate statistics. So in the case of an HK stack, it's a 2-parameter model. So basically, everywhere in your model parameter space, you can represent the probability as being proportional to exponent of -1/2 of the model parameter minus the expected value of the model parameter divided by the standard deviation of the model parameter, quantity squared, plus model parameter 2, let's say that's VPVS, minus the expected value of that model parameter divided by the sigma associated with that model parameter, again, quantity squared. And that gives you a probability density distribution, or density function, I should say, if you divide it by a normalizing factor, a constant essentially that guarantees that you're going to have an integral over all of the model parameter space of 1. Usually we ignore that factor simply because the peak is going to be the peak no matter what, and the shape of the function is going to be the shape of the function no matter what that constant is. So you can kind of ignore the constants and just go forward with the shape. Okay, so hopefully, Francisca, are there any other questions at this point?
Yes, actually.
Okay.
So the question is, what kind of variance in the estimates can we expect due to the space thinning? Can we use this estimate with a 2D kernel density estimate? Or sorry, can we use this method with a 2D kernel density estimate?
With a 2D kernel density estimate? Yes. Are you talking about 2D spatially?
Let's see if they follow up. Yes.
Yes. Yeah, in fact, the kriging approach was designed initially for 2-dimensional and 3-dimensional spatial representations. So it's possible, for example, if you expect one of your dimensions to have a different variance property than another dimension, you can also build in what's called anisotropy of the variance properties. But yeah, this is very much designed to do 2-dimensional, 3-dimensional. You can also do 1-dimensional, but it's rarely used for that. Representations of the variogram properties. Those can be different in the different dimensions if need be. And basically, you know, whatever variability you can build into the spatial representation of the variance of the properties, that's perfectly reasonable to use in a kriging interpolation. And in fact, it's highly encouraged if you have that information.
Okay, great. Thank you.
Great. Okay, so that basically brings us to the end of what I had for our lecture, and we can probably move on to the lab. There is a number of different files that I had uploaded yesterday, including a Jupyter notebook. I should caveat before we begin that I am a very novice Python coder, and this is my first experience with Jupyter notebooks. So hopefully everything will go okay with this. But we can go ahead and I believe we take 5 minutes. Is that right, Francisca, to get everybody sort of settled and situated? And then
yeah, let's do that. Let's take a 5-minute break. So I have 40. So let's come back at 1:45, and we will step through the laboratory. Oops, and I'm going to stop recording.